Hello again, this is Jerry Pinter and welcome to part 3 of our lecture for chapter 3. In this lecture we will learn about projectile motion. So first a couple of definitions. What is a projectile? A projectile is an object that moves through the air or space and is under the influence of gravity only with no other forces. A trajectory is the path through space that a projectile follows. So there are many examples of projectiles. For example, here we've got the guy kicking a soccer ball. So the soccer ball, after he kicks it, is a projectile as it moves through the air. A football player punting the football. The ball goes up into the air and comes back down onto the field. The ball is a projectile while it's moving through the air. Shooting a basketball. The basketball becomes the projectile. The human body can become a projectile. For example, here is a long jumper competing in a long jump where the athlete runs down the track, launches himself or herself into the air, and becomes a projectile until he lands in the pit here. A traditional example of a projectile is that of a cannon shooting a cannonball. So after it's launched, the ball shoots out of the cannon and becomes a projectile. The picture we saw in the first opening slide of this lecture showed somebody on a motorcycle actually going off of a jump and riding through the air. In that case, they're also a projectile. So one of our goals in this lecture is to be able to solve projectile problems. And in order to do so, we need to come up with a set of equations of motion for projectiles. So in almost all cases, a projectile problem starts with the projectile's initial launch speed and launch angle. So in this case, the example looks like a basketball that's being either shot, or it could be, a soccer ball being kicked or something like that. But the key thing is that over here at the initial launch of the ball, we know its initial speed. And of course, this is a velocity vector that points up at some particular angle, and this angle is called the launch angle theta. So what we're going to do to solve problems here is sort of a divide and conquer strategy. We are going to decompose projectile motion into two separate independent problems. One that involves the x or horizontal direction, and the other problem will be in the y or vertical direction. And each of these have their own set of equations that are going to describe the motion. So one of the first things we're going to do is take the initial velocity vector here. The initial speed is v sub I, remember it's at angle theta, and we're going to decompose this vector into its horizontal and vertical components, which we'll work with separately. So the horizontal component of the launch velocity, we're going to call that v sub I x. So this is the initial launch speed in the x direction, and using trig, this is just equal to v sub I, which is the initial launch velocity, times the cosine of theta. We can do the same thing to find the vertical component of the initial launch velocity. So v sub I y is equal to v sub I, which is again the initial speed of the launch, times the sine of the theta, of the launch angle theta. So we're going to use these two components to now come up with a set of equations for the x direction and the y direction. Now this looks at first, a bit tricky and complicated, but the good news is we actually don't have anything new. We're going to see the same equations that we've used up to this point in the course. We're just going to sort of assemble them separately. So let's take a look at the x direction first, since it's much simpler. In the x direction, meaning horizontal direction of our projectile, gravity has no effect on the horizontal direction of motion. Since gravity points downward, it's only going to affect the vertical component of the projectile. So in the horizontal direction, the acceleration for a projectile is always 0. So this simplifies things significantly. So there's really only two equations we need for the horizontal direction. The final x position of the projectile, in other words, how far does the projectile go? This is also called the range, is given by the initial position. And of course, this may be 0 if it's launched at the origin. And we just have that plus the velocity, initial velocity in the x direction, v sub I x, times the time. Now remember, v sub I x is given right here. It's v sub I, the launch speed, times the cosine of theta. The other thing, which is actually not really an equation per se, but it's just sort of a trivial fact, is that since there's no acceleration in the x direction, our velocity in the x direction is constant. In other words, the final x velocity is equal to the initial x velocity. And remember, that's given by this, v sub I cosine theta, and that's constant. So this is really the only equation we have to work with here in the x direction. Is to figure out the range, we're going to need to figure out the time. Now, how do we get the time? Well, that's where we're going to use the y direction equations of motion. So again, at first glance, this looks like a bunch of new equations for us, but it's not. These are the exact same equations as an object in free fall that we saw in the last chapter. So in the y direction, the acceleration is that due to gravity. So of course it's in the downward direction. So our acceleration in the y direction is minus g, and g of course is 9.8 meters per second squared. So our position formula in the y direction is given by final y position is equal to initial y position plus v sub iy, which remember it was found over here, vi times sine theta, times the time, minus 1/2 g delta t squared. Another equation we'll need is the final velocity in the y direction is equal to the initial velocity in the y direction, which again is given by this, vi sine theta, minus g times delta t. And again, of course, g is 9.8. The last equation here, which is often useful since it doesn't contain any time variable, is that the final y velocity squared is equal to the initial y velocity squared minus 2g times delta y, where delta y here is the displacement, how far the projectile has moved in the y direction. So again, our strategy for solving projectile problems is going to be to break the problem up into two different sub-problems. One for the horizontal direction using this information here, and then the other for the vertical direction using this set of equations here. And we'll go through some examples shortly in this lecture. One of the characteristics of projectiles is that they follow parabolic trajectories or paths through space. We won't go through the details of the mathematical proof here, but basically what we're doing in these steps shown here is just combining our equations from the last slide, and when we put them all together, we end up with the equation of a parabola, which you might recognize from your math class. So what this means is that when you take an object like a ball and throw it up at in the air at some angle like this, the path that the ball traces in the air is that of a parabola. Likewise, with the cannon down here, you can see it, different trajectories are shown here for different launch angles, but in all cases, these paths shown here are parabolic in shape. So let's now work through an example of projectile motion. So in this example, we have a cannon that's shot off the edge of a 50-meter tall cliff at a 25-degree angle as shown. The muzzle velocity or initial speed of the cannonball is 150 meters per second. So here's the picture of what's going on here. Here we have our cliff over here. You can see it's at 50 meters is the top of the cliff. Here's our origin down here. And so the cannon is shooting the cannonball off the cliff upward at a 25-degree angle. That's our theta here. And the initial speed of the cannonball is 150 meters per second. So the cannonball is going to shoot out like this. It's going to reach some maximum height here, and then it's going to start to fall. And as it keeps falling, it's moving still horizontally. And finally, it's going to strike the ground over here at some final horizontal position, x sub f. So we're going to basically answer 4 questions here. Part A is how long does it take for the cannonball to land? Part B, how far from the cliff does the cannonball land? Part C, what is the maximum height of the cannonball? And part D, what is the speed of the cannonball when it hits the ground? So let's start with question 1A, which was to find the time it takes for the cannonball to land. So for this problem, we're going to use the position formula for the y position, the vertical position of the cannonball. So this is given by the formula y final equals y initial plus initial y velocity times time minus 1/2 g times squared. So remember that the cannonball ends up on the ground, so its final y position is 0, all right, which is on the ground. Its initial position, yi, is 50. And remember that we can find the initial y velocity by v sub I times the sine of the angle. And remember, the angle is 25 degrees. The other thing we can do here in this last term, we know, of course, that g is equal to 9.8. So now we can plug in a few more numbers here. We know the initial velocity of the cannonball is 150. And sine of 25 degrees, you have to do that on your calculator, is 0.423. And over here I have 1/2 times 9.8, which is 4.9. So this middle term here, 150 times 0.423, turns out to be 63.4. So here's our, what's left of our equation now with all of our numbers in it. What I'm going to do here is just rearrange this so it's in a more recognizable form. I'm going to put the term with the square in it out in front. So I've actually moved this over to the left side of the equation. That's why we lost the minus sign there. Also, these terms here, I'm going to move those over to the left side of the equation also. So they pick up a minus sign. Okay, so all we're doing here is just rewriting this equation with the square term out in front. So we have 4.9 times time squared minus 63.4 times time minus 50 equals 0. Our goal, of course, is to solve for delta t, the time. Well, the only way to do this is to use the quadratic formula, because this is a quadratic equation. So remember the quadratic formula from math class. If we have an equation that looks like ax squared plus bx plus c equals 0, then x is equal to opposite of b plus or minus square root of b squared minus 4ac all over 2a. And of course, here our x is our delta t. All right, this is just the general quadratic formula. So plugging in our numbers, we can see that a is 4.9, b is negative 63.4, and c is negative 50. So I've just taken those 3 values and plugged them into this formula right here, and that's all shown here. I won't read this all out because there's a lot of numbers in there, but the rest of this is just some simple calculations on your calculator. And what we end up with is delta t is equal to 63.4 plus or minus 70.7 all over 98. So remember, there are always 2 solutions in solving a quadratic formula. One of them has the plus sign and the other has the minus sign. So when you do the plus here, you end up with 13.7 seconds. When you do the minus sign, you're going to get a negative number. And remember, you have to divide by 9.8. You're going to get negative 0.74. Well, we're looking for a time here, so we're going to choose the positive time solution, and that's the answer to this part of the problem. Let's move on to part B of this projectile problem. Find the horizontal distance the cannonball travels. Well, this is actually much easier than part A. We've already done the hard part, and that was finding the time. We know that the cannonball is in the air for 13.7 seconds. So to find the range of the cannonball, or in other words, how far it goes horizontally, remember that x final is just equal to x initial, which is 0, right? Because we're starting right here at the origin of the horizontal axis. And all we have to do is add vi sub x times the time. So remember, vix is equal to vi, which is 150, that's the launch velocity, times the cosine of theta. And so we have cosine of 25 is equal to 0.906, and then we multiply that by 13.7. So the product of these three numbers right here is 1,860 meters. So that's the distance, the horizontal distance that the cannonball travels before it crashes into the ground over here. There's actually an alternate solution, another way of solving part B that I'm not going to go through because it's considerably more complicated than what I just showed on the last slide. But this is just a reminder again that there are often multiple ways to solve problems in physics. This more complicated method uses the parabolic trajectory equation, which we derived a few slides ago. And plugging in all the numbers here, you can see there's quite a bit of math and there's another quadratic equation involved, but we get the same answer down here, which is nice to know that at least the methods are equivalent and consistent. Okay, so let's move on to part C of this problem. The problem asked, what is the maximum height that the cannonball obtains? Well, there are two ways to do this again, as is often the case. This way over here, I'm not going to go through. It's considerably longer and more steps. The better, shorter way to do this is the one shown here in yellow in the box. And the key thing to know to find the maximum height is that whenever an object is thrown up into the air or shot up into the air like a projectile, when it reaches its maximum height, its y velocity becomes 0. And think about this. This is this makes sense. If you throw something up in the air, in order for it to stop and come down, it has to reach 0 velocity. And where does it do that? Well, right at the peak. So we can use this sort of as a trick. We can use our equation here for final y velocity squared equals initial y velocity squared minus 2g delta y. Now what we're going to do here is we're going to call the cannonball at its peak, we're going to call that the final part of this problem. Obviously the cannonball goes past and ends up falling to the ground, but we're allowed at this point to define our final velocity at the peak. And the reason we do this is because we know what the velocity is at the peak. It's 0. So we also know what the initial y velocity is. It's the initial speed, which is 150, times the sine of the angle, sine of 25. So that's squared, and then we have minus 2g delta y. What we're going to do is solve for delta y. We're going to find out how far did this cannonball actually go upwards when it reaches a peak at when its velocity becomes 0. So all we have to do now is basically solve this equation here for delta y. So let's move this negative term over here, let's move it to the left side by adding it to both sides of the equation. This is just basic algebra. So we have 2 times 9.8 times delta y equals vi times 0.423 all squared. To solve for delta y, we are going to divide by 2 times 9.8. So you can see that down on the bottom here. I've also plugged in for vi. Remember, our initial cannonball velocity is 150 meters per second. Okay, so we can tap this out on our calculator, and we'll find out that the displacement of the cannonball to reach the peak is 205 meters. We have to be a little careful, though. This is not the final answer, because remember, this just tells us how far the cannonball went up from the cannon. This is its displacement. To figure out the actual maximum height of the cannonball, we need to add the height of the cliff to the displacement. So the height of the cliff, remember, is 50 meters. So we add 50 to our 205 meter displacement to get our final Y max of 255 meters above the ground. The last part of this projectile motion problem is part D, where we are asked to find the final speed of the cannonball when it hits the ground. So to do this, we're going to need to find both the X and Y components of the cannonball velocity as it hits the ground. We know that it hits the ground at a time 13.7 seconds after it was launched. So let's go ahead and first find the X velocity of the cannonball. Well, this is actually pretty simple because remember the velocity in the X direction does not change. Gravity does not affect the X direction. So the final X velocity is just equal to the initial X velocity, and that's equal to VI times cosine of theta. Remember, V sub I is equal to 150, that's the launch velocity, and the cosine of 25 is 0.906. So our X velocity is 136 meters per second. So, we can start to construct a picture here. The cannonball is moving horizontally at 136 meters per second. So now our next task is to find out how fast is the cannonball moving downward in the vertical direction. So to do this, let's use the equation final Y velocity is equal to initial Y velocity minus G delta T. So we know all these numbers here. We have V sub I is 150. You can see that I put it in down here. The sine of 25 is 0.423. This is, remember, V sub I times sine of 25. That is our initial Y velocity. That's the component that we found by V sub I times sine of theta. And then we have to say minus G, which is 9.8, and multiply by the time, which we've got from part A was 13.7 seconds. So our final, doing the math here, we'll see that our final Y velocity turns out to be negative 70.8 meters per second. Now, what does this minus sign mean? Well, this just means that the cannonball is falling. The velocity is pointing downwards, and that makes sense. The velocity was initially upwards, but of course the cannonball went up, stopped, and then came down. So here is our Y, or vertical velocity component of the cannonball. When it strikes the ground, it is going 70.8 meters per second, but this arrow, remember, is pointing downward, reminding us that it's falling. So our answer to the problem is we want to know what is the final speed of this cannonball. Well, we've got the two components. We've got the X component of velocity, and we've got the Y component. We need to add those together as vectors, but you can see that this is a right triangle, right? The X and the Y velocities are at right angles to each other. So this is the hypotenuse of the right triangle, gives us the final speed of this cannonball. So we're going to use the Pythagorean theorem. We know that V squared, that's the hypotenuse, is equal to this side squared, which is 136 squared, plus this side, 70.8 squared. So in order to figure out what V is, we have to take the square root of the Pythagorean theorem up here. So you can see we plugged in the numbers here, 136 squared, and here we have negative 70.8 squared. The minus sign will go away when you square it. And then you add these two numbers together after you square them and take the square root. And the final answer is 153.3 meters per second. That's how fast the cannonball is going when it strikes the ground. One of the interesting characteristics of projectiles is that a projectile that is launched horizontally will hit the ground at the same time as an object dropped from the same position. And you can see that in this stroboscopic picture here taken. This yellow ball was launched horizontally, and you can see it sort of follows this curved path here and strikes the ground over here. At the same time this was launched, the red ball was dropped. And this picture was taken in a dark room using a strobe light with the camera shutter remaining open. So every time the strobe flashes, it takes a snapshot of where the ball is. And you can see that at every instant of time, the two balls are in the same position and they hit the ground at the same time. So the next, what you're going to see next is a demonstration, a video demonstration that another physics professor made showing this exact demo. So notice when they get launched, when the ball is launched and dropped, watch very carefully and notice how they hit the ground at the same time. Now, what would happen if a bullet was fired and horizontally, and at the same time a bullet was dropped from the end of the gun? So here we have a rifle, and this rifle shoots a bullet out like this at extremely high speed, obviously. But at the same time we shoot the rifle, we drop an object, like another bullet, right here. Well, which one is going to hit the ground first? Well, let's go ahead and watch. There's kind of a neat video demonstration that was done on the show called Mythbusters. Another demonstration that's related to the last two that you just saw is when we aim a gun upward and have the gun fire and the object, the target, falls at the same time that we fire the gun. So in this example here, suppose you aim a dart gun at a coconut up in a tree. At the moment you pull the trigger, the coconut falls off the palm tree just by chance. Okay, so here's the you're down here, you're aiming, you're sighting this coconut up here, but as soon as you shoot the gun, the coconut just by chance happens to fall and starts to drop. Well, what happens? Well, the dart or the projectile actually strikes the coconut, exactly. And the reason for this is that if there were no gravity, obviously the projectile wouldn't curve at all. It would just go in a straight line because there would be no gravity to curve it downward. And of course, the coconut up here wouldn't fall either because there's no gravity. But since there is gravity, both are falling. And in fact, they both fall at the same rate, and they're both tracking each other. So here's another on the next slide, or the next video demo you'll see was done by MIT, where they use a stuffed monkey up in the tree, basically, and they shoot a golf ball at it. So I think you'll enjoy the video. The last thing we're going to do here with projectiles is to figure out how do we maximize the range of a projectile? In other words, at what angle should you throw, hit, or kick a ball to make it go farthest? So to do this, let's first of all, we're going to assume that there's no air resistance. This is going to make things much easier for us. So we're going to start with our equation in the x direction. The final x position is equal to the initial x position plus v sub I x times time, and v sub I x, remember, is the initial launch speed, vi, times the cosine of theta. So the next thing we can do, the next step here, is we can find an expression for delta t, because we notice we want to make this range as large as possible, but we don't have an expression yet for delta t here. So we're going to go to the y direction, the vertical direction equation, to find an expression for delta t. So remember that the final y velocity is equal to the initial y velocity minus g times delta t. So we can solve this equation here for time, all right? And the way to do this is basically we can move this g delta t term over to the left side, which gets rid of the minus sign, and we can move this v final y over to the right side, where it picks up a minus sign. And finally, we can divide by g. So doing the algebra steps, which I don't show, it's easy to show that delta t is just equal to sub iy minus v sub fy, that's the initial velocity minus the final velocity in the y direction, all over g. But there's a little trick here. For a projectile, that if we throw something up in the air, it comes down at the exact same speed that it went up with. So our final velocity is just equal to the initial velocity, but with a minus sign in front of it, because of course it's going in the opposite direction. Here it's going down, here it's going up. So we can replace this v final y with negative viy, and we have a minus sign here and a minus sign here. Those minus signs cancel, and we're actually adding viy plus viy. So we get 2 times viy in the top, in the numerator here, divided by g. And the next step is, remember that v sub iy is equal to the launch velocity vi times sine of theta. All right, so we've got an expression now for delta t, all this stuff over here on the right side. We're going to take this and we're going to substitute it in to this equation up here where we see the delta t. The result is this equation right here. The final x position of our projectile is equal to 2 times the initial velocity squared times cosine theta times sine theta all over g. Our goal is to make this the final x position. This is the range of the projectile. We want to make this as large as possible. So one thing we can do to make it a little more obvious is we can replace cosine theta times sine theta with a known trig identity. And you can look these up. You can look up a table of trig identities. And the one we're going to use here is called a double angle formula. Cosine theta times sine theta is equal to 1/2 times the sine of 2 theta. So we're going to replace this cosine theta sine theta with 1/2 sine of 2 theta. And notice the 1/2 in front here cancels the 2 here. 1/2 times 2 is just 1. So we end up with a reasonably simple formula here. The final x position is equal to the initial velocity squared times the sine of 2 theta divided by g. And our goal, again, is to maximize this. How do we make this number as big as possible? Well, remember that the sine function goes from -1 to 0 to +1. So the largest the sine of anything can be is 1. So when is the sine equal to 1? Well, the sine of 90 degrees is equal to 1. So we need 2 theta to be 90. And obviously that occurs when theta is equal to 45 degrees, because 2 times 45 is 90. So this tells us that the angle for maximum range of a projectile is 45 degrees. All right, so as shown here, when the baseball player hits the ball, if the ball launches off the bat at 45 degrees without wind resistance, this will maximize the distance that the ball travels. And by the way, when we do that, this sine of 2 theta just becomes a 1, and we have an equation here for the maximum distance of a projectile is equal to just the square of the initial velocity divided by g, a very basic and simple result. I'll just make a note here that due to air resistance, the optimum angle is actually less than 45 degrees, but we won't include that at this point.